Okay, in question 4, we're looking at nuclear fission and nuclear fusion. Okay, so in 4.1 we have got a nuclear equation to represent the fission of uranium-235. So this is the form of uranium that we use in nuclear power stations. Okay, so what we see going on there is, first of all, we have our nucleus of uranium-235, which we deliberately make unstable by firing a neutron at. Okay, so that nucleus absorbs that extra neutron to make uranium-236, which is extremely unstable. What happens there is that nucleus is so unstable it splits apart into two smaller nuclei, but at the same time it also is giving out some extra neutrons, in this case 3, though it's not always 3, and it's also releasing energy. I'm going to write those key points down. So the first thing to say is we are talking about a nucleus of uranium-235. Okay, it absorbs a neutron that we've deliberately fired at it. And therefore becomes so unstable that it splits apart. Forming, first of all, two smaller nuclei, three extra neutrons released, and also we were told they were barium and krypton, and also releasing energy. Okay. 4.2, we've now got to move it on and describe what happens in the process of nuclear fusion. Okay, remember, nuclear fusion in pretty much every sense is the opposite of fission. So this time we're starting with two small, or technically we ought to say light, as in not very massive, nuclei. And these join together. Whereas fission, we were splitting something apart. In fusion, we are joining together to make a heavier nuclei. Okay, and again, some of the mass is converted into energy. So this is also a process that releases lots and lots of energy. In the last part of the question, we're told that fission reactors are used in nuclear power stations, and we're hoping that in the future we'll be able to also have fusion reactors, which could use different isotopes of hydrogen that are called deuterium and tritium. And that deuterium is naturally occurring and can be easily extracted from seawater, and that tritium can be produced from lithium, which can also be found in seawater. Okay, in the table that we see next, we've got a comparison showing us the amount of energy that can be released in fusion and in fission from 1 kilogram of fuel in each case. Okay, and then to gain our marks, what we've got to do is to suggest two advantages of the fuel used in a fusion reactor compared with the fuel that would be used in a fission reactor. Okay, now this is a nice question because all of the information that we need is in the question. Okay, so the first thing that's better about fusion is that per kilogram of fuel it releases more energy. Which is obviously an advantage. The second advantage is that the materials that we would need, the deuterium and the tritium, are easily obtainable. Okay, both of them can be produced from seawater, which we have very large amounts of. Okay, we could also alternatively argue that the fusion produces very little in terms of radioactive waste compared to fission, which does produce a significant amount of radioactive waste, but fusion isn't intended to do that. Okay, so any two of those 3 points would gain you marks, and if you look at that, that is a quite compelling reason for why fusion would be much better for us than fission.